All right, we are now recording. Let me go on and get the PowerPoints brought up. Let me do screen share. And this, I think, is the PowerPoint we need. Okay. Can all of you see the PowerPoint? Or anybody see the PowerPoint? Okay, good. All right, there it is. All right, now, if y'all have no comments or anything, let me go over just a couple of things. I had emailed the records office just to see if they were through adding people to the classes because I still had some. And by the way, I wanted to find out, I think, Alea, you were trying to get in linear algebra too, weren't you? I didn't earlier this morning, but it may be there now. Have they added you or do you know? Okay, when did she say she added you? Last Thursday. Okay, it was not there. So I think you need to get back in touch with her if you've got that email because I didn't receive that email. I don't think. I don't recall seeing it. Email back and say you're still not able to get it on your portal and that I have not seen you on the roll of the class. So check again to make sure you got in. Okay. And while just a moment, Houston must have had to go out and come back in. So let me let Houston back in again. Okay. I already marked him here. Yeah. Okay. So, Alea, I was thinking that you're probably going to be the last one they added. Now, I know that last week they were having some difficulty adding people, and the reason for that was that financial aid takes over the system, and when they have the system, records can't do anything with it. So that may be why they didn't get you in last week, but they should have you in now because I believe financial aid has finished whatever they were doing. So check with them again to make sure you didn't get caught in the seam between records office having control and financial aid. It may be records thought they were putting you in and financial aid had control of the system and you didn't get in. So check with them again and make sure and tell them that when I last looked at it, which was this morning or sometime over the weekend, I did not see your name on the roll. I put you on the roll in my roll book, but you're not on the official roll that I could tell yet. It wasn't showing up on the thing. So if you'll do that. So anyway, I assume that they're pretty much through adding people. So what I've done is put you in my roll book, and then I got everything marked and graded and stuff. Of course, for this class, that's mostly your and James, since you're first time here, let me say this for you too. If you remember from when you took Cal 1 back in the fall, on Blackboard, we were using a different Blackboard back then, but the Blackboard, I have out there the syllabus, my locator card, which shows when I'm in class, out of class, teaching, not teaching, advising, not advising, those kind of things, lunch, those kind of things are all on the locator card. The research paper instructions are there. If you remember, we had one back last fall. We have it again. Can't get rid of those, okay? There's also, the PowerPoints. If you do use WebAssign, Esther, did you see that they did finally get or at least they told me, yeah, they it is okay, great. I want to make sure you can see it. The guy told me he put it in, but I hadn't looked myself. Okay, so the PowerPoints, the WebAssign key, class key, all that stuff's out there. A few oh yeah, I can't think what you call it, web links that either students have told me they found useful or I found and I wondered if they'd be useful, so I put them out there. Okay. In addition to all that, there is the link to the YouTube videos. Okay, so I don't know, James, if you've been able to watch those or not, but that would be a good thing to review to see where we are. We started in chapter 5. Maybe your Cal 2 class got this covered already. I think someone from that class said they did, but you had to sort of rush through it. Mine did not. Uh, we had so many technical problems once we left campus that we got way behind. So that's why we're doing chapter 5 right now. So this may be a review for you. So hopefully you can pick up and go from there. It seems like, okay, no, okay, there, WebAssign is available for you. Okay, I don't use WebAssign, but it's there for your viewing pleasure. You can look at it, you can use the problems, you can, um, use the tutorials, you can use everything on WebAssign. I just don't make any assignments on it. And the reason is, I explained this to the rest of the class, um, when I've tried to use it before, I spend more time trying to calm students down when they've had right answers and WebAssign has told them they had wrong answer. And the reason is WebAssign's looking for one specific way to write that answer. And you may have it in a perfectly correct way, and WebAssign's looking for a different way, and it'll say wrong. It's not wrong, it's just not in the form they wanted you to be in. And there's back when I was using it, there was no way that you could figure out which was which. So I finally quit using it, but let the students use it if they want to. It is a good product, except for that fact, and it has good tutorial. It has good problems that you can work on, and I think they'll help you walk through the problems. So the guy told me he put the due date for all of them. He put all the problems out there. He put the due date as the last day in July, so you can go back and review those anytime you want to. But none of them are due to me. They're all for your viewing pleasure, like I said. Okay. So what I do though is every class or every week, however you want to do it, please turn in at least one homework assignment, and those are from the book. Now, if you want to do a assignment, yeah, you can turn that into. I don't care where you get your assignment. Some of the people in the class, since they're transient students, may be using other books. They can do a problem out of their book. I don't care. Just let me know that you are doing problems. And the main thing I want to know is if you're having difficulty with the problems. Um, if you have a problem, you can't figure out how they got the answer, submit that to me and say, where am I making my mistake? And then I'll look it over and see if I can figure that out. Now, if it's a WebAssign thing, I might say, nope, you got it right. It's just they're looking for this answer, and you see how this is equivalent. So just give me something either after every class or once a week at some regular frequency, no further apart than once a week, but get me something so I can make sure you're staying with the class and able to participate. All right. Yeah, at least one problem from the text, unless you're having problems with more than one. Okay, and Cal, I believe, just showed up, so I'm putting Cal down. Okay. And by the way, the first assignment, the first day class assignment was to sign the syllabus page, that page at the last page of the syllabus. Either sign it or print it off with your name on it and send it to me. That was the first day's class assignment. And ever since then, it's been homework assignments. Yeah. Okay. No rush at all. Just get it to me at some point. All right. So what I was saying, I finally got everybody put down in the grade book and I got everything caught up. And this morning, I was finally able to get things put on Blackboard. Now, I can't put the homework assignment things on Blackboard. Blackboard's looking for a score on everything. And since these aren't scored, and I'll explain to you those people who have added later, what these do for you, if you, at the end of the term, I'll count how many, what I do, I'll show you. I put pluses on the grade book, okay? I'll count how many pluses you got. That's how much homework you turned in, and then I'll do a distribution of how those numbers look. And if you're at the very bottom of that distribution, I'll split it into, say, 5 equal pieces. Okay, if you're at the very bottom of the distribution, you just get your score. If you are further up, you may get, I may round a little bit more. And then further up at the top, you could, if you're a borderline, let me put it this way, this simply would put it this way. If you are in, say, the upper half of having turned in your homework assignments, okay, and you come out right on the borderline A, B, or B, C, hopefully no lower than that, right on that borderline, and you have done, I've got more pluses out there than blanks, then I bump you up to the next higher score, even though the round off wouldn't take you there. Okay. Now, that's only if it's close. An 81 will never bump up to an A. Okay. But if you're 89.2, and that would normally be a B, you get bumped up to an A. So that's what the homework will do for you. If you're solidly an A, you're solidly an A. And probably the reason you're solidly an A is because you did your homework. So the homework's going to help you both ways. It'll help you do better on the test. And if you don't do quite as well on the test and you turn in most of the homework, it may actually bump you up if you're borderline. So that's the main thing homework's going to do for you. The main thing is going to help you keep up with the course. All right. So I don't have anything out there on Blackboard yet for this class because I don't have any research paper turned in and we haven't had a test yet. So y'all can turn in the research paper anytime, remember? I actually had a couple turned in the month of May. And so a couple of people got the 2 bonus points. This what not in this class though. But this is now June. If you turn it in the month of June, you get an extra bonus point for turning it in June. If you turn it in July, you get your score with no bonus. Okay, so be sure to work on the paper. Several of you have turned your topics in to me. I appreciate that as well. Any questions? You choose anything that has anything to do with calculus, I would say. Okay. For instance, what's the name of this section that we're on? What's the name right up here on the screen? Riemann sums. If you're really interested in this good-looking guy named Georg Friedrich Bernhard Riemann, and you want to write on him, you can write on him. Or how do you use Riemann sums? Or anything else, any person, any theory, any application, any website you found that's really helpful in understanding what's going on in this course, you choose. It has to do with calculus. It can be historic, folkloric, it doesn't matter what. Just be sure you get me preferably a topic, but I definitely want a paper, okay? And the main reason to get me the topics, if someone else has already chosen that topic, I might say, well, wait, somebody else got that one, look for another one, okay? So the sooner you get me one, the sooner it's yours. Like I said, a lot of you have submitted topics already. All right, any other questions? All right, now, we left off last time. If there's no questions, I'm going to back up one slide. I thought I was going to back up one slide. And by the way, somebody, I can't remember if it was this class or the other class, told me some way that I could keep this window from showing up here. And I've tried it. Okay. Let me count, make sure I've still got 15 people. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah. Okay. They said, don't expand to full screen. I didn't, and the thing's still popping up there. The reason it pops up is that when someone enters the class, this is where that shows up. And for some reason, Zoom doesn't like that to show up. So Zoom puts this block there so the person's name, I guess, can't be seen by anybody else. And sometimes it can't be seen by me. So I have to say who this is. And when it fades out, maybe I can catch a glimpse of whose name it is. But then once it starts, it just keeps fading in and out. So I'm sorry about that. I've tried and tried. I can't get rid of it. Now I'm going to try this and see if it'll move it. I don't think it will, but I'm going to give it a shot. You can't see what I'm doing here. I'm moving my taskbar down to the bottom, and maybe with the taskbar down there, if the thing shows up, then it'll show up with the taskbar. And nope, it's still showing up in the middle. But if someone else goes out, comes in, something like that, then it may move it down there. All right. Anyway, so anyway, we are done, and I can't get the slide to progress or advance. I have to touch the screen first. Well, I went the wrong way. Well, nope, still going the wrong way. All right. We did example 1. Okay. Let's see. Jesus is here. Let me get Jesus in the room. Okay. All right. Jesus is here. All right. We should be up to whatever. See, it did move the block down a little way, so that's the best I can do. Okay. Let me make sure we should be at, yeah, 16. Got it. Okay. We did example 1. I'll back up a little bit more just so you can see how, well, this is so aggravating. Okay. There we go. There was example 1. Okay. Now, we had done something that looked a lot like this back in 5.2. Actually, what we did there was a thing where we did dy's, and the y as a function of x was y is equal to, no, I'm sorry, x as a function of y was x is equal to y squared, and that plotted like this, okay? And we did the part here, and we found out, and you'll need to go back, it was example 7 in 5.2, we found out, as they say here, I'll get there in a moment. Okay, from the region up here, this is where they come from here, that area was 1/3. And if you did glance at it when I was just going by there, the area under the curve, not outside the curve, was 2/3. And there is a reason for that, because the area between +1, 0 to +1 on y and 0 to +1 on x, that makes a square of area 1. So this part down here is 2/3. That part up there is 1/3. And this is what we used in example 7 in section 5.2. We did this part and found it to be 1/3. And now in what we just did last time, we found the area under that curve to be 2/3. And of course, those add to be 1. Okay. I'm going to wait just a moment for this thing to fade out. So the area of the region bounded by the graph of y is equal to x squared, and the y-axis for 0, y between 0 and 1, that was 1/3 for 2 reasons. We calculated that way last time, and we just found this area under here was 2/3 when we did example 1. So why they made such a big deal about that, I'm not sure, but they did. So any questions before we move on? All right. Oh yeah, and here we go again. Because the square bounded by 0 to 1 on x and 0 to 1 on y has an area of 1, 1 by 1 is 1, you can conclude that the area of the region shown in this figure, which we just did in example 1, was 2/3, and sure enough, that's what we got. Okay? And it doesn't matter, and they're going back over this again, which it seemed like they're beating to death. The subintervals do not have to have equal width. When we were doing 5.2, we generally found the subintervals to be the delta x to be b minus a over n. Well, you can choose other divisions there. Here's one they chose, and it came out with this area under here being 2/3, the same as what we did before. All right. Again, they're beating this to death. Okay. Now, This agrees, what we just said, with the limit found in example 1, even though that example used a partition having subintervals of unequal width. So it doesn't matter what partition you use, okay? What a partition is a breakdown of your domain, you might say, however you want to break it down, okay? That's called its partition. And this partition could have equal widths when we said delta x was equal to b minus a over n, or it could have unequal widths like we just did in example 1, okay? The reason this particular partition gave the proper area as n increases, the width of the largest subinterval was approaching 0. So anytime you have subintervals of equal widths, you need to make sure the largest one is approaching 0. If the largest one's approaching 0, the smaller ones have to have been approaching 0 much faster. And that's a key feature in the development of definite integrals. You may not see why yet. In fact, you may not see in the future yet, but this book makes a big deal about it, okay? So here's the definition of a Riemann sum. And note that the function f has no restrictions other than being defined on an interval from a to b. Now remember our restriction before, this function had to be positive anywhere between a and b. This one does not make that distinction, okay? So here's how the definition of a Riemann sum goes. Let f be defined, f is your function, on any closed interval a to b. Remember before it said it had to be positive on that closed interval. No, it doesn't anymore. And let delta, this is a capital Greek letter delta, it looks like a triangle, right? Delta, be a partition of a to b. Notice it didn't say a equal partition or anything else, just any partition between a and b. You just have to cover every interval between a and b. Given by a is going to be the first part of that partition. That's going to be your x of 0. And then the next partition is going to be at x1, at x2, at x3, at x4, finally till you get to x of n, whatever that x of n is, and that last one's going to be equal to b. So you've covered every bit of ground between a and b, okay? The delta x of I is the width of the ith subinterval. Let's say it was right in here, and that would be x sub I minus 1 to x sub I, okay? Somewhere in there, that is your delta x sub I. And every x sub I, here would be delta x of 1 would be x1 minus x0. Delta x of 2 would be x2 minus x1. Delta x of 3 would be x3 minus x2. Delta x of I would be x of I minus x of I minus 1. That is your width of the ith subinterval. The last one would be x of n or b, whichever you want to name it, minus x of n minus 1. That would be the width of the nth subinterval. Now, if c sub I is any point, we talked about this last time, any point on that ith subinterval, okay? It doesn't have to be the midpoint. It doesn't have to be one of the endpoints. Any point in the ith subinterval. Then the sum, and here's this Riemann sum, the sum from I going from 1 to n of f sub c sub I times delta x sub I. So this is the width of the ith interval. That's any point in that ith interval. And the sum of all those for all the i's going from 1 to n, that's called your Riemann sum, where x sub I minus 1, the left-hand n, is less than or equal to c sub I, and that's less than or equal to x sub I. That's your Riemann sum for the partition delta. Delta, remember, is a partition that doesn't have to be equal. It may be an equal partition, or it may not be. It just has to have every element covered, every value covered, okay? Now, the width of the largest subinterval, remember that's the one we're focusing on, the largest subinterval of that partition delta is called the norm of the partition. Now that's, to me, sort of a strange name for it, because norm usually means either perpendicular or broken down to be 1. This doesn't mean either one, it just means the norm of the partition, okay? That's the largest subinterval in that partition. And it's denoted by this double bars around the delta. That means whatever the largest partition is in delta, that's the norm of delta, and that's how you represent it. If every subinterval is of equal width, then the partition is a regular, and the norm is what we did before. Delta x is b minus a. That's your length of your region in x divided by n, so that gives you n equal subintervals, okay, n equal partitions. For a general partition, however, the norm is related to the number of subintervals in the following way: b minus a divided by the maximum, the norm, is going to be less than or equal to n, because you see, if delta is, if this symbol here, if this, if this is your norm, and that's the largest partition, then the b minus a over that largest partition is sort of like you take the n and move it here, the delta and move it there, okay? The norm and move it there. And then because this is the largest partition, you put it in the denominator, that's always going to be less than or equal to n, okay? Now, again, a lot of focus on things that in the future you'll probably forget that even was mentioned. But this book does a really focus. This is called your regular partition. This one down here is called your general partition. I can't get the cursor to show up. All right, let's move on. So the number of subintervals in a partition approaches infinity as the norm of the partition approaches zero. Norm being the largest subinterval on that partition. The number of subintervals approaches infinity as the norm approaches zero. That is, as the norm approaches zero, that implies your n is going to infinity. The converse of this statement is not necessarily true. For example, if you had a delta sub n, if that's a partition of the interval from 0 to 1 given by 0 is less than 1 over 2 to the n, that's less than 1 over 2 to the n minus 1, less than 1 over 2 to the n minus 2. Keep on going. So whatever your n was, let's say it's 7, 2 to the 7th, 1 over 2 to the 7th, this is 1 over 2 to the 6th, 1 over 2 to the 5th. I'm sorry, I didn't go high enough, did I? Okay, sorry. 1 over 2 to the, 2 to the 7th. I don't even know that one. Let's go to start saying I do know. 2 to the 4th is 64. No, 16. 2 to the 6th, I think, is 64. Yeah, 2 to the 6th is 64. So if this is 1 over 2 to the 6th, that'd be 1 over 64, and that's less than 1 over 32, and that's less than 1 over 16, that's less than 1 over 8, less than 1 over 4, less than 1 over 2, and that's less than 1. So here's a partition, a perfectly good partition. Let's see who came in. Daniel must have had to leave and come back. So I've already got him present, so hopefully we got everyone accounted for. Okay, so there's your partition. Now, does that meet the requirement? Okay, as n is going to infinity, okay, was someone talking to me or just got your microphone on? Okay. Here's the problem with this. As n is going to infinity, n can be getting as big as possible, and these things keeping smaller and smaller and smaller, but that doesn't mean that that first interval is going to get smaller, and it doesn't. It stays 1/2 no matter what you do to it. So you see, you can't say that just because the number of subintervals in a partition approaches infinity as the norm of the partition approaches zero. That's true, but you can't say as the norm of any partition approaches 0, that guarantees the n is going, or that set it backwards, So don't get confused. Again, usually this is not an issue, so don't focus on it too much. He's just bringing up an exception here. Okay, so let's move on. Well, I'm going to try to move on. All right, here we go. It's shown in figure 520, which is in your book. I believe we're over on page 308 now. Now, if you don't have a book and your author does not focus as much as we did, as this one does, don't sweat. Oh, here we go. Here's here it is at the bottom of the page here. Okay, here is figure 520. With that delta we just said, here is going to be your partition. Okay, and this is not one that meets the criteria. This is 1 over 2 to the 0th power. 2 to the 0th power is 1. That would be 1. 1 over 2 to the first is 1/2. 1 over 2 to the second is 1/4. 1 over 2 to the third is 1/8. 1 over 2 to the nth. This would be 1/16 down here. And take half of that, 1/32, 1/64, 1/128. You can keep on going. That, as n goes to infinity, the smaller ones definitely are going to infinity, but this big one up here at this n, it never changes. That is 1/2. It doesn't go to 0. So this is not, just the fact that n is going to infinity does not imply that this, the norm of this partition is going to 0. It does not. What we're dealing with is if the norm of partition is going to 0, then n must be going to infinity. So it's a one-way equivalency. It's not both ways. Okay. Again, they're sort of going overboard on it. All right. Now we turn to page 308, definite integrals. Okay. To define the definite integral, let's consider a limit. This limit is that norm. Remember, that stands for the norm. The norm is going to 0. You must have the norm going to 0. Then that would be the summation for I equal 1 to m of F sub c sub I times delta x sub I, just like we did before. If that limit exists, okay, to say that limit exists means there does exist some real number L, that limit, such that for any epsilon greater than 0, oh boy, this sounds like our good old derivative again, but now it's going the other way. There is a delta greater than 0. That sounds familiar. Such that for every partition, for that norm going to, as long as that norm is less than this delta, it follows that the difference between the limit and that sum is going to be less than epsilon. So what we did before in derivatives, we're sort of doing the same thing in your epsilon delta definition and we're heading toward integrals. Okay, regardless of the choice of what C you pick in that interval. Remember, it doesn't matter. It doesn't have to be the endpoint. It doesn't need to be the center point. It's anywhere in the interval x sub I. It doesn't matter, regardless of the choice C sub I in the ith interval of each of those partitions delta. Okay, again, a lot of blah, blah, blah. Okay, so here's that definition. We just said it. They provide it again. If f is defined, needs to be a function that is defined on some closed interval a to b. Now remember now, it's not required that this f be positive. Earlier, we required that. It doesn't anymore. Any f defined everywhere on the closed interval from a to b, at point A, at point B, it's defined everywhere in between. And the limit of the Riemann sums over the partition delta, okay, and the limit as that delta, the norm, the largest partition in that delta is going to 0, is the summation of I equal 1 to n of F sub c sub I times delta x sub I. You add that value up, basically the area under that rectangle. The height of the rectangle is F sub c sub I, and the width of the rectangle is delta x sub I. If that limit exists, as described earlier, then f is said to be integrable on that interval. Okay, now get this. Integrable, and this is an interval, so don't get them crossed up. Interval, and the limit is denoted by the limit as your norm is approaching 0 of the summation of I equal 1 to n f sub c sub I times delta x sub I. Now notice what we've done here. It may not be intuitively obvious, but think of it this way. Remember, this is the Greek letter, capital letter sigma. It stands for a sum of these rectangles. Height of the rectangle, width of the rectangle. And it's going from I equal 1. At I equal 1, you're at point A, the left-hand endpoint. When I is equal to n, you're at point B, the right-hand endpoint. So here, your summation now sort of stretches out and becomes this sort of S-looking figure. Not a very good-looking S. It's too skinny, and just a little curl at the top and bottom. That's your integral sign. Now, if I remember correctly, this is probably was developed, the integral sign, I think, was first used by Leibniz. I don't think Newton ever used that symbol. He didn't use dy dx either. You know, Leibniz came up with the symbology. Newton did integration, but he just didn't use that symbol. And this is a symbol for integration. It's basically this sigma symbol, which stands for S, sort of stretched into an S. For I equal 1, that's when the lower limit, when x equal a, to the upper limit when I is equal to n, you'd be at x equal b. Okay? And then your function goes here. Instead of f sub c sub I, it's just f sub x. And your delta x sub I becomes dx. As that delta x, as that norm goes to 0, the delta now goes from being, now this is a different delta, but it means that it's related. That delta goes to a d, incrementally, infinitesimally small delta. The limit is called the definite integral. I'm going to have to wait until the box goes away. It's going to fade out in just a moment, hopefully. Meanwhile, my cursor fades out. So hopefully it's going to move out of the way soon. Get out of there, folks. There it goes. Okay. The limit is called the definite integral of f from a to b. The number a is called the lower limit of integration. The number b is called the upper limit of integration. That's what a definite integral is. The indefinite integral, or the antiderivative, remember, had the same symbol here, but it didn't have numbers there. Okay? Now, though Riemann sums were defined for functions with very few restrictions, a sufficient condition for a function f to be integrable on a to b is that it's continuous on a to b. It doesn't have to be differentiable. No, just continuous. Most continuous functions are differentiable, except for those who have points or cusps. Remember, they can be continuous but not differentiable. All that's required here for it to be integrable, though, is that it be continuous, okay, on a to b. So here is the theorem that says that continuity implies integrability. If a function f is continuous on any closed interval a to b, then f is also integrable on a to b. That means the integral from a to b of f of x dx exists. Okay. Now, does that mean the reverse, though? If it's integrable, does that guarantee that it's also that f is continuous? Let's hold judgment on that until we get a little further. Okay. So here's example 2. Okay. Now we're going to go back and redo what we've already done. We're going to treat this just as if you didn't have these limits on it. What is the antiderivative of 2x? Anybody? Anybody? What's the antiderivative of 2x? You with me? X squared, perfect, okay? And then you're going to evaluate that from x equal 1 to x equal minus 2, or from x equal minus 2 to x equal 1. Now, they haven't told us how to evaluate that yet. We're going to get there. Let's just watch them do it, okay? The function f of 2x is integrable over the interval from -2 to 1. Of course it is. It's a polynomial function that's continuous, so therefore it's integrable. Because it's continuous on -2 to 1, because polynomial functions are continuous everywhere, from negative infinity to positive infinity. So it is continuous, okay? It is integrable, okay? Moreover, the definition of integrability implies that any partition whose norm approaches 0 can be used to determine the limit, okay? So we're not going to do it the easy way. We're going to do it the epsilon delta way, okay? So for computational convenience, let's define that delta, that partition, by subdividing -2 to 1 into n subintervals of equal width. So now your subinterval here is going to be, the delta x is going to be, this is any of your delta x's, are all going to be equal. B minus a divided by n. Well, b here is 1. Minus a minus 2, that would be plus 2. 1 plus 2 is 3. 3 divided by n. That's your partition. That's your delta x. That's your interval width. That's the maximum. That's the minimum. That's all of them. 3 over n. By choosing c sub I, you could do it anywhere you wanted to. They're going to use the right-hand endpoint. Doesn't matter. That usually is a fairly convenient one because on an equal interval, okay, that right one is going to be a very reasonable value there, okay? So your C sub I, that's your ith subinterval there, ith value for that thing on the right-hand side. Your A, remember, was -2, and then you're going to do plus your I times your delta x, where your delta x is 3 over n. So this will be -2 plus 3i over n. 3 from here, I from there, over n from up there. So there is your C sub I for every I on that interval, okay? For every partition on that interval, okay? And remember, your delta x is this, and there's your C sub I. So we're going to use these two features. I'm letting the box go away so I can show you a little bit better. These two features, this is where you're going to evaluate the f of x, okay? And this is the delta x, okay? So here's what it is. The definite integral then would be this limit as your norm is approaching 0. Of course, this is an equally spaced norm, so all those are approaching 0. The biggest included, they're all the same size. I equal 1 to n of f of c sub I times delta x sub I. Remember, that's your formula. That's what this stands for. Now, this, remember, is your f sub c, is your f of x. That's going to be 2x. So the c sub I we just had, remember, was -2 plus 3i over n. Remember, -2 plus 3i over n. You can't see it there because the box is in the way. I'll let the box fade. So there's your C sub I, -2 plus 3i over n. Your delta x was the 3 over n. So you plug that in here. That's where you're evaluating this function C. Go multiply. You're going to be, that is your x sub n. C sub I is your x. And you're going to do it. So let's go on and do it before I talk myself to death here. So it's the limit now. Let's change and make the n approaching infinity because those are the same. They're interchangeable. Del, your norm is approaching 0. That means your n is approaching infinity. Of summation of I equal 1 to n of f sub c sub I times delta x. They really should have an I here. They left it off. They should have, well, the delta x's are all the same. So that's why they left it off, okay? So let's plug in what those are. That's the limit as n approaches infinity of the summation of I equal 1 to n. Remember, this is 2 times that value is going to be your C sub I, -2 plus 3i over n times your delta x, which is every delta x of I is 3 over n. All right. All right. Now let's see what we've got. We've got a two-term polynomial. Everything is multiplied by 2 times 3 over n. So that's 6 over n. Okay? So let's rewrite that way. So the 6 over n, 2 times 3 over n, there's no I dependence on that. You can pull that outside of the summation. Not outside the limit. The limit is dealing with n's, but outside the summation. Let's see. Anita's here. Excellent. Okay. Let me get Anita marked present. All right. You know, folks, thank you so much. This has to be my best attending class since we've gone virtual. I mean, last spring and this time. Only 2 people are absent, right? No, 3 people are absent right now. Amina's not here yet, I don't think. Laron's not here yet, I don't think. I believe they were sharing a computer last time, if I'm right. And then Angelica, we haven't seen from the beginning, which is a little concerning. So she was in my class last time and came fairly regularly. Okay, so hopefully she'll show up. But out of 20 students, 17 of you are here. Excellent, excellent, excellent. Yeah, well, 16 are here now, but 17 have been here at some point. Okay, so what we did, we pulled out the parts that did not depend on I outside here, and that's 2 times 3 over n. That's your 6 over n. Okay, and here's the parts that did depend on I. Minus 2 plus 3i over n. Okay, now if you remember how we do our summations, the summation of a sum, okay, sorry, I can't get my cursor. You can break this as summation of -2 plus the summation of 3i over n. Well, the 3 over n could come outside that second thing. Well, what's the summation of -2? It's -2 times n. Okay, remember that back at the beginning of 5.2. Okay, and this one, a 3 over n, you could pull that on the outside, and the summation of I is I times I plus 1 over, what was that? 2, yeah, I times I plus 1 over 2. Okay, so let's do that step. Well, I thought I could do that step. I don't know why it hangs up. There it goes. So here we have it. The summation of the limit as n goes to infinity of the 6 over n comes on the outside. The -2 comes outside this one. And then you have the summation of I equal 1 to n. That's just going to be n. Okay? Because it's 1 plus 1 plus 1 plus 1 plus 1 plus 1 n times. That's going to be n. So this will be a -2n. And this will be the 3 over n comes on the outside. And the summation of this is going to be I times I plus 1 over 2. Okay, so let's do that step. There's your 6 over n. This is -2n, like we've already said. This is 3n times, there's your n times n plus 1 over 2. Now, where are we going to go from here? Let's bring the 2 on the outside here. I think I also want to divide out the n here, okay, because those are not necessary anymore. They'll cancel out. The 2 comes out here, so that gives me a 2/3 out here and an n plus 1 in here. Here's a -2n, and this is a plus 3 over 2 times n. If I can do that in my head, that would be minus n over 2, I believe it is. That would give you a minus n over 2 plus 3 over 2, okay? Doing this in my head, so hopefully I've got it right. So this minus 2n adds with this term here. You cancel out these 2 n's, and that gives you 3 halves n. So it's a plus 3 halves n. That's a minus 2n. So it'd be a -1/2 n plus, and now you would just have 1 over 2 times 3, so it'd be 3 halves. Okay. plus 3/2. And that's all multiplied by 6 over n. Okay, let's let them write it down so we can see. All right, here's what they did. Yeah, okay. They, and this may be a little easier, they divided this n into that one and this n into that one. They left this 3 over n alone. Okay, so that gave them a minus 12 here, which is what we were heading toward. And this gives them, when you divide that n out, you wind up with a 3. Oh, and by the way, 2 will go into 6. Well, no, let's not go there yet. Well, yeah, I guess we have to. 2 will go into 6 3 times. That leaves you 3 times 3 times n plus 1 over n. Okay, well, the 3 plus 3, the n, okay, 3 times 3 is 9 times n here. That will be canceled out. So that gives you the plus 9 here. And then what you have left over is 1 over n. Okay, because your 2 went into the 6, the 3 times 3 is 9, and that would give you 9 over n. So there's the 9 over n. So the limit of this, as n goes to infinity, that goes to 0. Because 9 over n, as n gets very, very, very large, that's going to 0, and you're left with a minus 3. So the limit of this is going to be a negative 3. And there we have it. Boy, that's a long way, folks, but it's doable. Every step of the way, it's doable. Now, if you weren't here for the earlier classes, you really need to go back and review those and see where we got those formulas, but they're all in there. Okay. The good news is after this section, I don't think you're ever going to need them again. Okay. Until, well, I don't know. I won't say never, but leave it alone. Because the definite integral in example 2 is negative, what does that mean? It does not represent an area of a region because areas are by definition always positive. But what it does say is that this region, here's this function, f of x equal to x, it goes from down here through the origin, because when x equals 0, f is 0, y is 0, up to here. And if you're going from x equal minus 2, which is over here, it's way down here underneath the box, to 1, well, it's up here. Well, what's the area there? Well, this is a negative area because this part is below the x-axis. That's a positive area here, and when you add those two areas together, the negative, which is bigger, to a positive, which is smaller, you wound up with a negative number. And that's how we wound up with negative 3. Definite integrals can be positive, negative, or 0. Seems like a lot of work to go out and get nothing from it, but it can be. For a definite integral to be interpreted as an area, the function has to be continuous and non-negative. So we're getting away from the concept that it represents an area unless you consider this part down here to be a negative area, and then you can still think of it that way. Well, I can't show you because this is below the x-axis. So you can think of it that way, but basically just get away from thinking of areas. But the only way for it to be an area is f must be non-negative like we did before. So this goes to the next theorem. The definite integral as an area of a region, if f is continuous and non-negative on the closed interval from a to b, then the area of the region bounded by the graph of f, now remember f is non-negative now, the x-axis and the vertical lines x equal a to x equal b is simply that area, the definite integral from a to b of f of x dx. Okay, if you aren't thinking this now, you should be. Please let us not have to do those limits anymore and those i's and the n's. What can we do? Well, remember this one that we had before? This was sure enough it, the limit from a to b, whatever that antiderivative of f is, you evaluate that from a to b. Okay, I'm going to wait for this box to get out of the way. It's going to fade out in a minute, hopefully, so you can read the caption here. Here it goes. You can use the definite integral to find the area of a region bounded by the graph of f, the x-axis, and x equal a to b, as long as f is always non-negative in that interval a to b. Down here, it wouldn't work. If you were down here, you would have to then count this as a negative area and add it to the positive here. That's a different issue. Okay. As an example of that theorem we just stated, 5.5, consider the region bounded by the graph f of x equal 4x minus x squared. And the x-axis is shown here. Because f is continuous, it's a polynomial function, it's continuous everywhere, and it's non-negative on this interval from 0 to 4. Because when you put a 0 in here, you get 0, f of x would be 0. You put a 4 in for x, this would be 16 minus 16, that would be 0, but everywhere in between that, you're positive. So this will work for that region right there. Will not work down here or down here, and that function keeps going there. But for this region here, it does give you the area. Because f is continuous and non-negative on that closed interval, negative 0 to 4, the area of the region is given by the antiderivative, or the definite integral, from 0 to 4, 4x minus x squared dx. Now, please don't have us do that the other way. Ah, good. You can evaluate a definite integral in two ways. You can use that limit definition, or you can check to see whether the definite integral represents the area of a common geometric region, such as a rectangle, triangle, or semicircle. I really don't want to do either one of these, okay? Yeah, you can do that, okay? Now, we just worked example 2. They're now ready for example 3. If you got our book, this is on page 310. It says, sketch the region corresponding to each definite integral, then evaluate each integral using a geometric formula. Ha! All right. So, how would you do this? What is your function here? Someone answer. It's pretty simple. What is the function here? Can anyone see that? What's your function? It's really easy answer. Don't be scared of an easy answer. It's easy. What's your function there? It's the constant function 4. Alpha of x is equal to 4. Well, if you were to plot that, let's just imagine you do an xy axis here. X equal 4 would be up here. It's a horizontal line at x equal 4. And you're going from 1 to 3. So here's 1, and there's 3. The width here is 2. 3 minus 2, 1 is 2. The height here is 4, from 0 to 4. So you got 4 by 2 is 8. Hey, you can't get much easier than that. That's what this definite integral represents. Without doing any limit formula, without doing anything else, you have just discovered that. Okay? Let's see how they did it. There it is. There's f of x equal 4, constant function. You're going from 1 to 3. That's a width of 2, a height of 4. 2 times 4 is 8. They haven't given you the answer yet, but we'll get there in a minute. How about this one? Now you're going the integral from 0 to 3 of x plus 2 dx, okay? Well, the function here is x plus 2. That's going to be a straight line, y-intercept of 2, and slope of 1, right? And you're going from 0 to 3. Well, here's 0 here, 3's over here somewhere. What do you have? You have a trapezoid, okay? If you double that trapezoid, flip it on top of itself, so to speak, you have a rectangle. Well, what is the area of that rectangle? It would be, the base is 0 to 3, so that would be 3, and the height would be, remember this started at 2 here, and it went up to 2 plus 3 is 5 here, so 2 plus 5 is 7. So 7 times 3 is 21. Take half of that and you get 10 and a half. Well, let's see how they did it. Here we go. All right. The height here is 2. The height over here is 3 plus 2. Did I say 7? 5. I'm sorry. I was adding 2 to 5. Forget what I just said. 2 plus 5. No, yeah, okay, I was right. I think I said it right. 2 plus 5 is 7. So if you flip this trapezoid over itself and did it up here another 2 units up and came across here, you would have exactly the same trapezoid up here, okay? And it would be 3 by 7, I said it right, is 21, and half of that would be 10 and a half, okay? So that's the area there. All right, let's go back. How about this one? The integral, definite integral from -2 to 2 of the square root of 4 minus x squared. Well, if this is your f of x is equal to 4 minus x squared. So think of that as y is equal to 4 minus x squared. Okay? Now, square both sides of that, and that would give you y squared is equal to 4 minus x squared. Well, then let's add the x squared to the y squared. You get x squared plus y squared is equal to 4. Does anyone know what that gives you? A circle of radius 2. X squared plus y squared equal 4 is a circle of radius 2. Well, you only have half of the circle because this is a positive square root. So you only have a semicircle from here like this, from -2 to +2. You're not the bottom half, that would be a minus square root. You're the top half. So what is a circle of radius 2? Its area. Pi r squared would be a circle. That would be pi times radius 2 squared would be 4. So it'd be 4 pi. That would be the whole circle. Half the circle would be 2 pi. So we think the area of that will be 2 pi. Let's see what there it is. This is a graph. The square root of 4 minus x squared would be half of a semicircle. I mean, it's a semicircle, half of a circle of radius 2. The area of the entire circle would be pi r squared, where r is 2. Pi times 2 squared is 4. And then take half of 4 and you get 2. Okay, so 2 pi would be that area. Let's see what they found. The first one, the eighth here, is a region of height 4, width 2. So it would be the area of that rectangle. 4 times 2 is 8. Okay. You didn't have to do any limits, any summations. You just figure it out because of geometry. Don't worry, they're all not going to be this easy or this abstract either. Okay. On the second one there, that forms a trapezoid. The region is trapezoid with altitude 3, the parallel bases of 2 and 5. The area of a trapezoid, which I just sort of gave you, was 1/2 the height. That's it. That's the width. I don't like to call it height. That's the width of that trapezoid. That happened to have been, in this case, 3, I believe it was. And then the sum of the bases is 2 plus 5 is 7. So 1/2 of 3 times 7 is 21. That would be 21 halves, or half of the, and that's 10 and a half. They left it as 21 halves. Okay. Does that make sense? Okay. Let's do that last one. This region is a semicircle of radius 2. The formula for the area of a semicircle is exactly half the area of a circle. Area of a circle is pi r squared, so half of that would be 1/2 pi r squared. I'm waiting for the box to go away so you can see that is indeed the area of a semicircle, 1/2 pi r squared. So that integral from -2 to 2 of that would be area of the semicircle, which is 1/2 pi r squared, r being 2, Be 4 pi, half of that is 2 pi. So there is your answer, just like we got. Now, again, this isn't the bulk of calculus. This is just showing you how this relates to geometry. Okay. In a few minutes, hopefully, we will get to actually how we do these definite integrals. Can't wait. Okay. The variable of integration in a definite integral is sometimes called the dummy variable because it can be replaced by any other variable without changing the value of the integral. Okay. Whereas before we called it the independent variable, like that was really independent, had something to do with integration and differentiation. That was pretty important for it to be independent. In integration, it disappears basically with you doing definite integrals. If you were doing indefinite integrals, that x shows up. So don't throw it away. But here, this could be x plus 2 dx. It could be t plus 2 dt. It could be stickman plus 2 d-stickman. It could be anything you want it to be because it's going to disappear on you. That integral would have, those two integrals have the same value. Okay? Now, that got us through page 310. Let's move on to 311. Properties of definite integrals. I don't know what page it is in your book if you have a different one. Here is really where we're going to start dealing with how to do definite integrals. So get these properties down, nail them so that you may be able to use them anytime you want to. This definition of definite integral of f on the interval from a to b, the definition specifies that a be less than b. Okay, when you're doing the interval, a is the left-hand side, b is the right-hand side, and you're doing on that interval. A needs to be less than b. However, it's convenient to write the definition to cover cases in which either a is equal to b or a is greater than b. Now, this is a little bizarre, so hang on to it, and hopefully it'll start making sense later. Okay, geometrically, the next two definitions seem reasonable. I'm going to wait until this box moves out of the way. Hopefully it's moving out of the way soon now. For instance, it makes sense to define the area, get out of the way, the area of a region of 0 width and finite height to be 0. So if A is equal to B, that means your first point is the same as your last point. So that's the thickness of 0. No matter how high you are, 0 times any number is still 0. So if A is equal to B, your definite integral will always be 0. Always. Okay? So here's definition of two special definite integrals. Okay? If f is defined at x equal a, then the integral from a to a, in other words, your width is 0 of f of x dx is always going to be 0. Because no matter how big the f is, when you multiply it by a thickness of 0, it's going to be 0. So that one's simple. Now, here's the other one that may not be quite as obvious. If f is integrable on some interval from a to b, then the integral from b to a of f of x dx is minus the integral from a to b of f of x dx. Now that one may not be quite as obvious why that's true, but just take the word for it. It is true. If you are integrating from a to b and you get some value, if you went from b to a, you're basically negating that. That's what they're telling you. It's the opposite of that. Okay. My arm waving isn't going to make it any clearer. Just remember that. If you flip the limits of a definite integral, flip the sign. If it was negative, it becomes positive. If it was positive, it becomes negative. It flips the sign. If you flip the limits, you flip the sign. Just remember that. So let's evaluate. And here's example 4. They're not skipping any, are they? So let's evaluate each of these definite integrals. Anyone want to tackle this one? The integral from pi to pi of sine x dx. Anybody? Are you still there? It's zero, absolutely, because here your a's are the same. The integral from a to a is zero. The integral from pi to pi is zero. It doesn't matter what follows that. It could have been sine to the 17th power. It's still going to be zero. Okay. Now, this one depends on your having paid attention to the last example. This is the integral from 3 to 0 of x plus 2 dx. Can anyone tell me something about this integral? May not be the absolute answer yet, but what can you tell me about it? Here you're going from a high value to a low value. If you want to flip that around to make it something we're more used to, like the integral from 0 to 3 of x plus 2 dx, what would you have to do to that integral? Make it a negative. So this would be the minus of the integral from 0 to 3 of x plus 2 dx. And if you remember that one, that was that trapezoid. Remember? Exactly that trapezoid. And that came out to be 21 halves. So this one would be negative 21 halves. So you don't have to go back and reinvent the wheel. If you remember that was the answer before, it's the negative of that. And you're absolutely right. Because the sine function is defined at x equals pi, which is defined everywhere, and your upper and lower limits of the integration are equal, which they are, you can just write right off the top. I got to wait till the box fades out here. Sorry about this. It'll fade out in a moment or two or three. Get on out of there. Here it goes. The integral from pi to pi of sine x dx is 0, just like you said. Okay. On the b part, the integral from 3 to 0 of x plus 2 dx is exactly the same as that given in example 3b, except that the upper and lower limits are interchanged. So what you do, you just write that as the negative of this one that we do know the answer to. And that answer was 21 halves. Now, so the answer for this one would be negative 21 halves. And that's exactly what we've got here. You didn't have to do anything. It just remember that we had already done that integration earlier geometrically. All right. Maybe we're a step closer to really doing them the way you need to do definite integrals. Let's see. So here's figure 525, and this is on the bottom part of page 311 if you're following in the book. Okay. In figure 525, the larger region, okay, I know other classes have told me when I turn away from the microphone, I'll fade out. Let me put my book in front of me. That example 4 we just did, if you want to see that, especially those of you who do not have this text, if you want to see how this text did it, go to larsoncalculus.com. You don't need a code. You don't need the class key. You don't need anything. Just go to larsoncalculus.com, find example 4, section 5.3, and you can see them work through that entire example. Exactly what we did, probably in more detail. Okay? Now, here's what we're getting at here. In this figure here, you have some function f of x, and it's going from a to b. And this happens to be positive everywhere between a and b. So you can talk about this definite integral from a to b of f of x dx as being the area under that curve. From a to b, area under f of x dx, because f is positive everywhere. Now, they don't say why, but they just say they did. they split the area from A to B into two pieces, one from A to C and the other from C to B. Okay. Now, I can't tell you why they chose C there. I wouldn't have chosen it there. I think if I were doing this, I would have chosen it at the minimum value, which would be right maybe here somewhere. It doesn't matter where the C is. They just chose a C somewhere. Looks like about midway. It doesn't have to be midway. It could be anywhere in between A and B. Okay. Now, because we know from looking at this that this area plus this area is equal to the whole area. I mean, that's just intuitively obvious, I hope. Okay. Well, what does this area represent? This one, right? Goodness, there it is. This one. That would be the integral from A to C of f of x dx. And this area over here would be the integral from C to B of f of x dx. That's the same f over here. And here's what it's getting at. The integral from a to b of f of x dx is equal to, always equal to, if that's defined, this is defined. The integral from a to c of f of x dx plus the integral from c to b of f of x dx. Basically just saying, if you divide it anywhere, you could, excuse me. Are y'all awake yet? Sorry. Have to do that every now and then just to make sure everybody stays awake. Okay, I'm just kidding. Okay, because the line segment has zero area, that's from C to C, that is zero area, follows that the area of the larger region, I guess that's this one. I'm sorry. The larger region, meaning the pink region, the whole pink region, is equal to the sum of the areas of the two smaller regions. Makes sense. So here's theorem 5.6, which states that in math speak, if f is integrable in three closed intervals determined by a, b, and c, then the integral from a to b of f of x dx is equal to the integral from a to c of f of x dx plus the integral from c to b of f of x dx. Now that makes sense when c is in between a and b. Perfect sense. Actually makes sense when it's, well, as long as everything's defined, it could be on the other side too, but then one of these would flip over and be negative. So we won't go there yet. Okay. So here's example 5. Now this is one that you might have a little bit of problems with because this is the absolute value function. And the absolute value function, remember, is always a V-shaped function. And when you write down what the function absolute value is, it's a piecewise defined function. As long as x is positive, and you know x is positive, the absolute value of x is x. So anytime, but this is the integral from -1 to 1. X is not -1 at this lower interval. It isn't, okay? It's positive everywhere from 0 to 1. So break that out and do the integral from 0 to 1 of x dx. That's going to be part of that absolute value function. That's going to be the positive part, okay? Now, when x is negative, like from -1 to 0, then the definition of absolute value of x would be the opposite of x. Because x is negative, absolute value has to be positive, so that becomes minus x. So here's a piecewise defined function. So integrate its left-hand piece this way, integral from -1 to 0 of minus x dx, plus the positive part over here, integral from 0 to 1 of x dx. Okay, now, what would be the area under here? A minus x, when x is negative, this is going up like this. We know what the absolute value looks like. It goes up like that. And what's the area under there from -1 to 1? Well, the width is 1. It's a triangle whose width is 1 and whose height is 1. Well, a triangle is exactly half of the square or the rectangle that makes it up. In this case, it happens to be a square. The area of that square is 1 and half of that would then be 1/2. Same thing here, that would be another 1/2. These two add to 1. Okay. And they didn't show you why. They just said it's 1/2 plus 1/2. But that's because of your areas of those two triangles. Let's see if they will show you a picture. 1/2 plus 1/2 is 1. Good. I'm glad they wrote that down. They skip the steps that need a lot of explanation, and then they're sure to put in the one that you know that 1/2 plus 1/2 is 1. They show you that step for sure. All right. I'm making fun of them. All right. Top of page 312, we're going to get to the properties of definite integrals. Okay. Finally, we're getting to the place where we can start actually evaluating these things. We'll need to have these properties down. Remember that the integral from same limits is always 0. And the limit from A to B is the opposite of the limit from B to A. So just keep those two in mind. Here are some more properties of definite integrals. If f and g are both integrable functions on the same interval A to B, and k is any old constant k, it could be positive, it could be negative. It could even be 0, though we don't usually do it with 0, but it could be 0. It could be rational, it could be irrational. It could be a fraction, it could be a decimal. It could be a square root, it could be pi, it could be any k. Then the function kf and f plus or minus g are also integral functions on A to B. And anytime you add a constant to a function, the function's integrable, you can take that constant, pull it outside the integral, okay, and just do the integral of from A to B of f of x. Because I already told you it's an integral function from A to B. So pull the k on the outside. Positive k, negative k, 0k, rational k, irrational k, it doesn't matter. Okay. Now, here's another property. And this is sort of the thing that we did by dividing the areas, remember? Only this is a little different because there are different functions here. So, same type principle though, the integral from A to B of f plus g, f of x plus g of x, or f of b minus g of x. It doesn't matter which way you do. That's equal to the integral from A to b of f of x, and then keep the plus or minus in the same order, the integral from A to b of g of x dx. Okay? So, maybe they'll show you a picture of that one. Let's hope they do. Note that the property 2, I'm going to wait till that block, that rectangle fades out here. Please fade out fast. One of these days it's going to go. There it goes. Note that the property 2 of this theorem can be extended to cover any finite number of functions. So if you had a plus h plus a j plus a k plus, just add them all up and split them into different integrals. Okay? Still works. So here's example 6. They've shown every example in this section. That's rather unusual. So here's they want you to evaluate the integral from 1 to 3 of minus x squared plus 4x minus 3 dx using the following. Now, this is a little nuts, but it's okay. They're going to tell you what the integral is from 1 to 3 of x squared. It's 26/3. No verification, no explanation. They just tell you it's 26/3. And they're also going to tell you the integral from 1 to 3 of x dx is 4. No definition, no why. They just tell you it is. And the integral from 1 to 3 of dx, just dx, is 2. Okay? That's what they're telling you. And they're true on all of them, but they don't tell you why. We'll get to that later, a little bit later. All right, so what we do, let's take this integral here. Let's pull out the minus 1 and put it on the outside. So that would be a minus 1 times the integral from 1 to 3 of x squared dx. We're going to split this into this integral plus this integral minus that integral. Remember, that was our second feature back in the last here. If you have a sum or a difference, just split them into different integrals. So that's what we're going to do here. We're going to make this a the integral from minus x squared dx plus the integral of 4x dx plus the integral minus the integral of 3x dx, or 3 dx, I'm sorry, 3 dx. But we're going to take the minus and pull it outside that one. So that'll be minus the integral from 1 to 3 of x squared. Well, that's what this is. So this first part is going to be minus 26 thirds. Okay. Now, the second part, that was the integral from 1 to 3 of 4x dx. Well, pull the 4 on the outside. So it would be plus 4 times the integral from 1 to 3 of x dx. Well, that's 4. So that's 4 times 4 is 16. So minus 26 thirds. Wait, somebody, is this, who is this? I didn't see it. Did y'all see who that was that just came in? Did anyone see that? Who is that? Morgan. Okay. Okay. You were here before. Okay. Want to make sure I got your present. Okay. Yeah, Morgan already. Thanks. Okay. So let's go back and review this again. Minus 26 thirds plus 4 times 4 minus 3. Oh, yeah. On this last one, it's a minus the integral of from 1 to 3 of 3 dx. Well, let's pull the 3 on the outside. So minus 3 times the integral of 1 to 3 of dx. Well, the integral 1 to 3 of dx is 2. So minus 3 times 2 is negative 6. This was a positive 16, remember, so that gives us a positive 10, and this was a minus 26 thirds. So hang on to those numbers, and let's see what we get. Okay, so this will be what they've done. Wrote down the first integral again, and break that into 3 pieces. Integral from 1 to 3 of minus x squared dx, plus the integral from 1 to 3 of 4x dx, minus the integral, or plus the integral from 1 to 3 of negative 3 dx. I don't know why they didn't pull the signs out, but that's okay. What they've written is exactly true. So the next step, pull the minus sign out here. That'll be minus the integral from 1 to 3 of x squared dx. Pull the 4 on the outside, plus 4 times the integral from 1 to 3 of x dx. Pull the minus 3 on the outside, you get minus 3 times the integral of dx. But we know what each one of those pieces were, so that's what they did next. Minus the integral of this, plus 4 times the integral of that, minus 3 times the integral of dx. But we know each one of those from up here. So it's a minus 26 thirds, plus 4 times 4 is 16, minus 3 times 2 would be negative 6. And this is fading in, so I'll have to wait until it fades out again. Negative 26 thirds, it's going to be a plus 16, or plus 4 times 4. I don't know how it's going to express it. Yeah, plus 4 times 4 minus 3 times 2, and that adds to be 4 thirds. Okay, that was a plus 10, which would be 30 thirds, minus 26 thirds is 4 thirds. Yes, got it done. 4 thirds was our answer. Now, they didn't tell you how they got these. That's what we're going to do next. So hang on to that thought. Now, there's one more theorem here. Any questions on this example before we leave it? I know it's a lot of arm waving, but hopefully you're following this okay. Let's see what that last theorem says. If f and g are both continuous functions on the closed interval from a to b, and 0 is less than f, in other words, f is always positive, but f is also always less than g, which means g is always positive. For all that interval from a to b, for all x's in between a and b, then the following properties are true. First, the area of the region bounded, the area of the region bounded by the graph of F and the x-axis. Here's your F here. It's always positive, and from A to B anyway. And G is always greater than F is from A to B anyway. Okay, looks like G may be dipping down here and get below it, but that's okay. From A to B, G is always greater than F. Okay, now the area bounded by the region bounded, the area of the region bounded by the graph of F and the x-axis between A and B must be non-negative. Well, the reason is F is always non-negative. So therefore its area has to be non-negative. Okay, so that's always a positive area. Second, that area between the x-axis and F must be less than or equal to the area bounded by the graph of x-axis and G. Why? Because G was always greater than or equal to F, so its area has to be greater than or equal to the area under F. Now, if they were exactly the same function, they'd be equal everywhere, so that would be an equality. Otherwise, if G is ever greater than F any place, then the area will be greater. Okay, so that's all this is saying. The dark pink area is less than the light pink area, when the light pink includes everything in the dark pink. Okay. Those two properties are generalized in this last theorem, theorem 5.8, the preservation of inequality. If F is an integrable function and non-negative on the closed interval from A to B, then it is the integral from A to B of f of x, because if f is always non-negative, when you integrate from A to B, that's always going to be non-negative. So this is going to be greater than or equal to 0, or 0 is less than or equal to that. Now, if f and g are both integrable on that closed interval A to B, and f is always, for every value x, either less than or equal to g, every x in the interval A to B, then the integral, the area under f, is always going to be less than or equal to the area under g. If g is always greater than or equal to f, then the area under g is going to be greater than the area under f. So hopefully that's pretty obvious. They call this preservation of inequality because if the functions follow that, their integrals follow that. Okay? And this is saying if f is non-negative, that means it's positive. So the integral of f is going to be positive. Okay. Any questions on that? They don't do an example with it. They just end with that theorem. So I think that's the end of the slideshow. So let me give you the homework exercises here. And remember for today, if you want to do at least one of these odds, you can do any one you want to. But number 3 is at Calc Chat and Calc View. Now, remember at 3 also has the answer in the back of the book. And for those who are fairly new to the class here, here's what I always say. Number 1, try to do the problem. Look in the back of the book to see if you got the right answer. If you got the right answer, move on. You don't need to do anything else. If you didn't get the right answer, or if it's not in the form they have in the back of the book, you then again go to calcchat.com. And that's located at the very top of your page here, calcchat.com. You see it? Okay. This is a heavy book. Okay. So go to calcchat.com. Now, if they do a lot of blah, 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 and you still can't figure it out, if it's like number 3, it's also at calcview.com. Now, they don't show that website here, but there it is here, calcview.com. Okay? And you can see a more description of how to work that problem. Now, not all of them are like that, only the ones that are in red. But when you have one of those in red in that problem set, notice there's a QR code right there. You can take your phone and go to the QR code. It'll read it, or your laptop, or your pad, if you have an iPad or stuff like that. Read the QR code, and it will take you right to calcview.com, and you can see them work out the problem. So do number 3. It's both at CalcChat and CalcView. Do any of the odds 5 through 9. They're all at CalcChat. 7's at CalcView. Do either 11 or 13. They're both at CalcChat. Do any of the odds 15 to 25. They're all at CalcChat. Okay. Flip a page. Do any of the odds 27 to 35? They're all at Calc Chat. 29's at Calc View. Do any of the odds 37 to 43? They're all at Calc Chat. 41's at Calc View. Then do any of the odds 45 through, I'd say 49. They should all be at Calc Chat. 51 is a problem they say you can think about doing, okay? It should be at Calc Chat. You can check and see. And the same thing with 53 or 55. So I'd say for those three, any of the odds, 51 to 55, you can think about doing and look at Calc Chat and see how they do them. Then exploring concepts. Do any of the odds, either 57 or 59, they should both be at Calc Chat. And then there's a verifying a rule at 61, that should be at Calc Chat, and it says using different methods, that 63 should be at Calc Chat. Then you can do either 65 or 67, they're both at Calc Chat. There's a true false, a couple of them, 69 to 73. They should be at Calc Chat, okay? 75 should be at Calc Chat, and now you get into sort of some of the more esoteric things. If any of you are math majors, you may want to look at number 77, that's a proof, because when you get into your upper level math courses, you're probably going to be doing more and more proofs. So you want to look at 77. If y'all are going into engineering, most engineers couldn't care, I couldn't say that, less about proofs. So you can do those if you like, just to get the better understanding. That's up to you. You can think about doing 79 if you'd like. 81 is finding values. You can do that if you'd like. That should be at Calc Chat. You can think about doing 83 if you'd like. That should be at Calc Chat. And then 85 is the last one there. It should be at Calc Chat. You don't have to do all those, but might want to take a look at those. Now, I really want y'all to keep up with my time for me, because we got more than an hour to go, but I'll get to talking away and forget about it. I only have 5 minutes between this class and the next class, and so this one ends at 2:25, I believe. The next one starts at 2:30. So don't let me go past 2:25. Someone stop me if I start going too hot and heavy. Now, what I'm going to have to do now, I probably should have done it before, I forgot to do this. I'm going to probably get out of screen sharing for just a moment, because I've got to go out there and pick up a new PowerPoint. Okay. You may not see that. In class, I would always have my students, don't let me forget to turn that back on. Okay, we're recording again. We're still in Chapter 5, Integration. We're now in, it won't advance until I click on it. Okay. All right, 5.4, the fundamental theorem of calculus. Does this sound important to you? Yes, it is. This is going to tell us how we can do those definite integrals in a much simpler way, from trying to get geometric things. Those are not going to be easy to come by, only few and far between. Or going through all the limits and the summations. Oh, what a pain. Oh, y'all may not think so, but I do. Okay. Fundamental theorem of calculus is going to be your good friend. So let's get it. What we're going to do is evaluate definite integral using the fundamental theorem of calculus. Thank you so much. It's about time. We'll understand and use the mean value theorem for integrals. That's going to be an application of this that's maybe not quite so much fun, but it's still okay. Find the average value of a function over a closed interval using that mean value theorem. Now, different books call it different things. Some books call it Fundamental Theorem of Calculus Part 1 and Part 2. This book calls it Fundamental Theorem of Calculus and the second Fundamental Theorem of Calculus. So however your book calls it, these are interchangeable. It's two different, they look fairly different, and they are. They're hitting on different issues. Okay, and then the next thing we'll do is understand and use the net change theorem. And yeah, that's the last thing in this section, the net change theorem. That's not a huge deal, but we'll hit it before we leave. All right. So here's the first part of the fundamental theorem of calculus. In some books, it's called Part 1. You now have been introduced to two major branches of calculus. What you did last term, differential calculus. What you've been doing so far this term, some of you did last term, integral calculus. But at this point, the two problems might seem unrelated, but there is a very close connection. Well, we know one connection. Integral calculus is taking antiderivatives. So yeah, they're related in that way. But the connection was discovered independently, they say, by Isaac Newton and Gottfried Leibniz, and stated as the fundamental theorem of calculus. Now, I'm going to say this. I hope it's not going to bias you in any way, shape, or form. I do not find their little illustrations here all that instructive. I know what they're talking about because I know what they're trying to say, but I don't see that these really make it a lot clearer. If you do, fantastic. But here we go. Informally, now this is informally, the theorem states that differentiation and definite integration are inverse operations. Okay? I would have almost said indefinite integration, but I know what they're meaning here. They're inverse operations. If you think back to your earliest encounters with mathematics, this could be kindergarten or elementary school. After you learn to count, you use your fingers and all like that, then they taught you to add, and you probably still use your fingers. But once you finally got that addition down, you thought you had it knocked, and then they turned around and said, now let's subtract. And subtraction undid addition, and addition undoes subtraction. Okay? So you finally got that down. And you thought, well, now I've got it knocked. No, you didn't. They introduced multiplication. Well, sure enough, you had to learn all a bunch of new tables, flashcards, whatever, however you learned it, you learned multiplication. And then you say, finally got that down. And they said, no, now let's undo multiplication. And we use division for that. Now, much, much, much later, you probably ran into raising numbers to powers. Okay? X squared or 7 squared. Okay? 3 squared, raising it to a power. Okay, got that figured out now. But then they turn around and teach you how to do roots, radicals, which undoes powers. Okay? So you see, all through your life in mathematics, you've done operations and then you've undone operations. They call those inverse operations of each other. And then, not too long ago, for some of you, you probably did pre-calculus. And in pre-calculus, they taught you how to do a function and then find the inverse of that function. What's the inverse of the function? The function that undoes the first function. So again, inverse operations. Now we're moving up another notch. These are not just operations, well, they sort of are, but integration and differentiation are inverse. Really, I mean, you're getting out of algebra into calculus, and they're inverse operations in calculus. In the same sense that multiplication, division, roots and radicals, whatever, are inverse operations of each other. Now, this is, they said, to see how Newton's and Leibniz might have anticipated this relationship. Here they consider some approximations. And again, I just do not find these all this instructive. They're every bit of it true, but I think I'm just missing what connection they're trying to make here. Now, remember back early on when we were doing differentiation, we talked about 2 points on a curve, and the line that connects those two is the secant line. And the secant line, the slope of the secant line was change of y, the rise, over change of x, the run. Delta y over delta x. Okay? Now, if you let the far endpoint get closer and closer to the first endpoint, then that secant line gets closer and closer to being the slope of the tangent line. So the tangent line, I would say, is a dy dx. They still call it delta y over delta x. You can't really tell you that. The delta x now is 0. You can't divide by 0, but you can do a dy dx where the limit of that delta x is going to 0. Okay? Now, here then they said, here's an area of a rectangle. Okay? A rectangle's area is its width times its height, right? Length times width. Okay? The height here is your f of x, or your y, or your dy in this case. That's the height here. The width here is your delta x. So the area of that rectangle is delta y times delta x. Yeah, we'll buy that. Okay? Now, the area under this curve here is the delta y anywhere along this curve, not the entire length, but anywhere along the curve, times some other smaller delta x. And you add all those things together, that would be the area under the curve. Now, the trouble with this is they don't define what the delta y. Here they showed you delta y. Here they didn't show you delta x because they couldn't. It went to 0. Okay? Here they don't show you delta y because it was varying all along the curve. The delta x you could sort of imagine here, but they don't even show that either. But it's the sum of your delta x and delta y under that curve. Okay? Okay, we see that. It says they have an inverse relationship. Well, inverse in the sense this is division and this is multiplication. But that's kind of a stretch, isn't it? Maybe not. Maybe it makes perfect sense to you. It just, to me, leaves a lot to be desired. But we'll leave it alone. Now, the slope of the tangent line, using the quotient delta x over delta y, which was the slope of the secant line. So the slope of the tangent was the limit of that as the delta x goes to 0. Similar, the area under the curve was defined using the product delta y times delta x, and that was the area of a rectangle. It's only you take smaller and smaller rectangles, and then you let, as delta x goes to 0, your delta y just becomes your y at that value of x. That's the best I can do here, folks. So at least the primitive approximation stage, the operation of differentiation and definite integration appear to have an inverse relationship in the same sense that multiplication and division do. The fundamental theorem of calculus states that the limit processes used to define the derivative, which I was talking about, and the definite integral, I think your Riemann sums, preserve that inverse relationship. Okay, in a sense. So here's anti-differentiation and definite integration. Throughout the chapter, you've been using the integral sign to denote an antiderivative or a family of functions when you didn't have limits, or a definite integral, which just represented a number when you did have limits. Okay? The use of the same symbol for both operations makes it appear they are related. Yeah, they better be. In the early work on calculus, however, it was not known that the two operations were related. And I did not realize that. I thought one followed the other pretty simply. The symbol, that integral symbol, was first applied to the definite integral by Leibniz and was derived from the letter S, which stands for sum. Leibniz calculated the area as an infinite sum, therefore the letter S. Now, a lot of books follow that rather than the way we've been doing it. Okay, we'll get to those S's when we get to infinite series in chapter 10, I believe it is. I hope we'll get there. Okay, here's theorem 5.9, the fundamental theorem of calculus. If you think this is important by the name, you're absolutely right. If a function f is continuous, that's all that's required. Function f be continuous on some closed interval a to b, And this capital F is an antiderivative. Remember, we did that back in 5.1 or 5.2? Antiderivative of that little f on the integral from a to b. Then the integral from a to b, the definite integral from a to b of that little f of x dx is just this antiderivative first evaluated at b minus evaluated at a. That's it, folks. That's the connection between antiderivatives or indefinite integrals and definite integrals. They took us through the limits and the sums and all that kind of stuff. I don't want to say forget it, but guess what? You don't have to do it anymore, at least until test time. Okay. The following guidelines can help you understand the use of the fundamental theorem of calculus. Okay. All right. Good deal. We have just a little less than an hour left now. Provided you can find the antiderivative of f, and that's not always a simple thing, by the way. It's most functions you can find a derivative for. There are some functions really hard to find an antiderivative. In fact, some are impossible. You now have a way to evaluate a definite integral without having to use the limit of a sum. Thank goodness. Oh, no, I shouldn't say that. When applying the first fundamental theorem of calculus, the notation below is convenient that the definite integral from a to b of f of x dx is its antiderivative, capital F of x, evaluated from a to b. Just bring these over just like this, which means take the f of x evaluated at b minus f of x evaluated when x equals a. So here's how we're going to do that. Let's do the definite integral from 1 to 3 of x cubed dx. Okay? Now, what's the antiderivative of x cubed? Does anyone remember that was a long time ago, last week I believe it was, that we did antiderivatives? What's the antiderivative of x cubed? How do you get it? You bump up the exponent by 1, so the 3 becomes a 4, and divide by that new exponent. So that would be x fourth over 4. So the definite integral from 1 to 3 of x cubed dx would be the antiderivative of x cubed, which is x4 over 4, evaluated between the 1 on the lower side, the 3 on the upper side. So you put in the upper first, 3 to the 4th power, 81, divided by 4, minus 1 to the 4th power, and you put in the 1 here, that's 1/4. So 81 fourths minus 1/4 would be 80 fourths, that's 20. Oh my goodness, could it be that easy? Don't you want to go back and do the limit of the sums? That's so much more fun, isn't it? No, that's it. It is not necessary to include a constant of integration in C in the antiderivative because you're subtracting the difference away, and this would have had the same C as that one did, and you subtract C minus C is 0. So if you did this, that's exactly what they do here. The definite integral from a to b of f of x dx would be capital F of x plus C evaluated from a to b, which would be capital F of b plus C minus capital F of a plus C. This C and that C are exactly the same. This is a plus, this is minus a plus. Those add to 0. It's F of b minus F of a. So guess what? With definite integrations, you do not have plus C's anymore. With indefinite integrals, you always have a constant of integration. Definite integrals, you do not. All right, so let's evaluate each of these definite integrals. Okay, you remember how you do the antiderivative of x squared? Anybody? Please say yes. Antiderivative of x squared. We just did it with x to the third, and it was pretty easy. So that becomes x cubed over, yeah, times 1/3, or x cubed over 3 minus, and how do you do the antiderivative of minus 3? Minus 3x, exactly. So this would be x cubed over 3 minus 3x, right? Evaluate that from x equal 1 to x equal 2. So plug in the 2 first. 2 cubed is 8 over 3, so that would be 8/3 minus 3 times 2 is 6. 8/3 minus 6. Minus 1/2, I'm sorry, 1/3. So 8/3 minus 1/3 would be 7/3. That would be, and then minus a minus 3, okay? That would be plus 3, okay? I'm losing my memory here, so let's go on and see how they do it. That's what you got, x cubed over 3 minus 3x, evaluated from 1 to 2. So plug in the 2 first, and you get 8/3 minus 6. That's 2 times 3 is 6. Minus, when you plug a 1 here, that would be 1/3 minus 3. But that following a minus sign, so it's minus a minus, so it's a plus. So this would be 8/3 minus 1/3. 7/3 minus 6 plus 3 would be a minus 3. So 7/3 minus 3. Well, 3 is 9/3. So 7/3 minus 9/3 is negative 2/3. I hope. Yes, and that's what they got. Okay, negative 2/3. Did everybody see that? Now, again, when you're doing your evaluations, take your time. You can either pair them up like this, or you can change signs here, but whatever you do, be very careful with it. Now, this is what I tell students sometimes, and it's not really fair, but I say the whole purpose of a minus sign in mathematics is to trip you up. It's just something to trip over. And a lot of times you will, because you're going to forget to change some sign somewhere or another. So be very careful when you're doing your things. Write them out carefully. And this becomes 8/3 minus 1/3, which is 7/3, minus 3, minus 6, plus 3. Minus a minus is plus 3. That would be a minus 3. Minus 3 is negative 3/3, plus 7/3 is minus 2/3. Now that's how I do it. If you have a better way, do it. As long as it's right, is fine. So let's go back and look at the previous one. Okay, how about this one? What would be your first step to solve this one? Would you start doing the antiderivative of square root? Please say no. What would you do? I would first rewrite this as the definite angle from 1 to 4 of 3 times what? X to the 1/2 power. Perfect. Okay. Now, also, I think about that same time, I would pull that 3 outside the integral and just deal with the x to the 1/2. So that's what we're going to do first. So let's go over here and see how they do it. They first write this, and they did exactly what I said. Pull the 3 outside the integral and do the definite integral from 1 to 4 of x to the 1/2 dx. Okay? Now, how would you do this integral now? You tell me. Add 1 to the exponent, and 1 is the same as 2/2 plus 1/2 is 3/2. So that becomes your new exponent, x to the 3/2, but that new exponent becomes your denominator. But since it's a fraction, rather than dividing by 3/2, I multiply by 2/3. Remember, multiply by the reciprocal. So you multiply by 2/3, the 3 then is going to cancel out, and that gives you 2 times x to the 3/2. evaluated from 1 to 4. So let's see if that's what they get. Yeah, there's a 3 on the outside, and they do the 3 to the 2 halves, x to the 3 halves, divided by 3 halves, evaluate them 1 to 4. We're not going to evaluate yet. Let's clean it up a bit, and that gives you, see the, yeah, the 2 here moves to the numerator, the 3 in the denominator, the 3's cancel out. That gives you 2 times 4 to the 3 halves power minus 2 times 1 to the 3 halves power. Well, what in the world is 4 to the 3 halves power? How would you do that? I would do the 1/2 first. 4 to the 1/2 power is the square root of 4. What's the square root of 4? Please say 2. Okay. And then you cube the 2. Okay. First take 1/2 of this, not 1/2 of it. The square root of 4 is 2. Then cube that, you get 8. 2 times 8 is 16. So this is a 16. Do the same thing here. The square root of 1 is 1. 1 cubed is 1. Minus 2 times 1 is minus 2. So what did I say this one was? 16 minus 2. That should be 14 if I did it right in my head. Let's see what they got. Yes, there they go, 14. Does everybody see that? And again, take your time, make sure you understand every step of your calculation, okay? Now, let's go back and see what the third one was. Oops, too much. Okay, this one. Oh my goodness. What is that? What's the antiderivative of secant squared? Does anyone remember? Antiderivative of secant squared. Uh-oh, I got to talk with your trig teacher. No, your Cal 1 teacher. Antiderivative of secant squared. Anyone remember? Derivative of tangent is secant squared. So the antiderivative of secant squared is tangent x. So that would be tangent x evaluated from 0 to pi fourths. So that's where we'll begin this one. Okay? The antiderivative of secant squared is tangent x, and we'll evaluate it from 0 to pi fourths. Okay? Now, tangent of pi fourths, anyone remember what that is? One. Very good. Okay. And what's tangent of 0? 0. And 1 minus 0 is 1. Oops. Oh, look at that. They skip lots of hard steps, but then they put 1 minus 0 is equal to 1. I'm glad they wrote that in there for you. Okay. It's pretty incredible what they choose to write and not write. Now, I want to point a couple things out to you. Okay. I know this is bizarre. Remember what we said about your functions here. The functions you're trying to integrate, all that's required is they be continuous. Okay. Now, this function here, x squared minus 3, polynomial function, continuous everywhere. It really doesn't matter what the limits are. You can do this for any limits you put on there because they're defined everywhere. Now, this one is a little bit maybe of a little problem, but not really too bad. The square root of x is continuous. It's just not differentiable everywhere because the square root of x is half of a sleeping parabola. And if you did the minus, it would be the other half. Well, this point right here would not be differentiable, but it is continuous, so it didn't matter where you put those. But they were really nice to you and kept it on one side or the other. They kept it on the positive side. That was a nice, smooth, continuous function there. However, this one was not. Secant is not a continuous function. Now, it happens to be that secant squared is really not either. It looks maybe like it is, but it's really not, because secant squared, and in fact, all of your trig functions except sine and cosine are discontinuous. Remember tangent? I'm going to do it with my curve here. Starts low, goes up and goes high, and then you start back low again, goes up and goes high. It's discontinuous at your half pi's. So you could not have had this going from, say, 0 to 3/4 pi. That would not work, because secant squared or secant, secant squared, and tangent squared are not defined at pi halves. So you could not integrate over that, because your functions has to be continuous in this interval. So they snuck this one on you, but they were right about it, because this is within the interval where they're continuous. But it would not be continuous if you tried to do from 0 to 3/4 pi. It's way too early in the course for you to recognize that, but I did want to point it out to you. Okay. So there was example 1. Any questions? By the way, I forgot to turn my page. And example 1 was top of page 319. Okay. Now, finally, they get to a place they're skipping 2 examples. Example 2 and 3. What you think? Do you think we need to go back and do those? I would say so, but I'm going to leave it up to you. You want to do examples 2 and 3? Yay or nay? Okay, let's do them. Now we go to the whiteboard. This is what y'all been dreading, looking forward to all day, right? Me writing on the silly little whiteboard here. Okay, now what I'm going to do, I'm going to move this. You can't see it. It's my taskbar. I'm going to move it to the top. And since this is going to be really almost traumatic, let's take a quick break. I'm calling it a bladder break, because I would like to not be uncomfortable much longer. Let's take a quick break and we'll be right back. I'm going to turn off the recording for now, but remind me to turn it back on when I come back in. I'm going to keep Zoom up, but I'm just. All right, we're recording again. Before we get recording, were there any questions on anything we've done up till now? None? All right. Here is example 2. Okay. And we're ready to draw here. I guess we better do it. So here is example 2. I'll begin up here. And this is going to be an integral. And again, my drawing sort of stinks. And it's going to go from 0 to 2. Of the function here is the absolute value function. 2x plus 1 . I was not looking forward to this because I'm so slow at this. Absolute value of 2x plus 1 dx. Okay, there's our issue. Now, I want to know how you would approach it. Where would you begin? When we have those problems that are a little bit stranger or unusual, what's usually our first step? Okay, yeah, you're jumping, okay? What I was getting to, remember when we had x, the square root of x? Before we tried to do anything, we rewrote it. This one also, we want to rewrite. This is my f of x, okay? I'm not going to call it f of x, but I'm going to come over here somewhere, how about right here, and write what we mean by the square of the absolute value of 2x plus 1. It is plus, not minus, is it? Yeah. No, it's a minus 1. Look at that. You let me get away with it. You're going to have me do the problem completely wrong, weren't you? And not going to say a word to me and let me get it wrong, and then you're going to laugh your way to the bank, weren't you? I know you, okay? That is not a plus, that's a minus. How in the world I did that, I don't know. But it's your fault, by the way. What do we mean by 2x minus 1? Absolute value of 2x minus 1. Well, this is a piecewise defined function. And this is rather strange pieces too. So I'm going to put it's called a brace here. Okay. Well, what does that mean? Well, that's 2x, whatever's inside the absolute value, is 2x minus 1 anytime that 2x, this seems crazy, but this is how it's defined, that 2x minus 1 is positive, right? Now, you could put an equal sign there. It doesn't matter, okay? That's what it means. If that thing inside the absolute value bars is positive, that's exactly its value, okay? So anytime the thing's inside there, that's its value. But when the thing is not positive, it's the opposite of that. So this would be minus, oh goodness, that's way too long of a minus, okay? Let's see if we can get that, cut down the size here. Okay, whoops, that's not what I wanted. Okay, now I'm going to not put parentheses here. It probably would be more instructive to do it, but it's going to be the opposite of that. So it'd be a minus 2x plus 1 anytime that 2x minus 1 is less than 0. Oh, goodness, that's ugly. All right. Now, I don't like that 2x minus 1 being less than, blah, blah. Let's go on and figure out what this is. Okay, let's do this inequality first. Add 1 to both sides, and that would give us a 2x. I'm just going to make it equal now. 2x equal 1, right? And then divide both sides by 2, and you get x equal 1/2, right? Do you buy what I'm doing here? So instead of writing all this down, this thing right here, okay, I'm going to do this. This is true anytime x is greater than 1/2, and this is true anytime x is less than 1/2. Is that okay to do? We just solved this inequality and found out that's equivalent to 2x minus 1 greater than 0. That would be when 2x is greater than when x is greater than 1/2. And when 2x minus 1 is less than 0, that would be x less than 1/2. Okay, so is it all right for you to, if I just change it here so I don't have to rewrite all that? I'm just going to put x greater than or equal to 1/2 and x less than 1/2. Is that all right? That's what we just did. So I'm going to erase this and this and that, and then rewrite this is x greater than or equal to 1/2. This is x less than 1/2. Now, there is our piecewise defined function. Okay. Now, based on what we did, what was it, a couple of theorems ago, let's break this integral now into the limits from 0 to 1/2 and use this part for that, because that would be less than 1/2. and then we'll do another part from 1/2 to 2, and then we'll do this part. You see what we're doing? We're breaking this down because this is a different definition from 0 to 1/2. That would be this definition. And then between 1/2 and 2, you would use this definition. That's what a piecewise defined function does. So I'm going to change this to be the integral. That's supposed to be a curve there, and it's not very curved. From 0 to 1/2 of this function, negative 2x plus 1. Yuck, that's an ugly 1. Okay. Sort of goes along okay for a while, and then it just completely botches up. It's me, okay, I'm talking about. Okay, dx. Now, I really should put that in parentheses so you don't get it confused. I'm going to do it. I just don't draw parentheses well. Okay, plus, that got you from 0 to 1/2. So the second integral is going to take you from 1/2 to 2. Because all those values of x's are greater than or equal to 1/2. So here is the argument now, 2x minus 1. Now I really should put that in parentheses too, dx. Just keep getting uglier and uglier, don't we? Okay. Now, this is a 0 down here. That sure doesn't look like one. Let me make it look a little more like a 0. Okay. I'll try anyway. It's a little more like a 0. All right, let's see if we can do this antiderivative as it is. Does anyone know what the antiderivative? Let's forget about the minus sign now. What's the antiderivative of 2x? Last week, you ought to have been saying this. X squared, and only got a minus sign, so this is going to be a minus x squared. Perfect, very good. Okay, and what's the antiderivative of dx? 1 dx. Oops, I said the minus x squared, but didn't write the square. Okay, and what's the antiderivative of 1 dx, or just dx? Antiderivative of 1. X, perfect, perfect, perfect. And this is evaluated from 0 to 1/2. There's your definite integral there. Okay, plus, now, this is going to be a lot different. It'll be a little bit different. I'm going to open this one with a bracket just so we can keep track of it. What's the antiderivative of 2x? I think you already said it. What is it? Was it that dx squared? But this doesn't have a minus sign in front of it, so it's just an x squared. And what's the antiderivative of 1 dx? Only this does have a minus sign, so that would be minus x. And this one's evaluated from 1/2 to 2. Okay, do y'all follow what's happening here? You split it into two integrals, different argument, different f's inside the integral, did those. They're similar but different, okay? And then we're going to evaluate it. So this first one, we're going to evaluate when x equal 1/2. Well, that minus sign is a minus sign, so it doesn't change here. And when x is 1/2, x squared is, someone tell me. 1/2 squared is 1/4, right? Yay or nay? Help me, somebody. Okay. Plus, ooh, that's ugly. When x equal 1/2, that's just plus 1/2. Now, here's one of my favorite things of doing this. When you have a polynomial here and you got a 0 here, minus 0 squared is 0 plus 0 is 0. I don't have to write anything else down for that one. That was the easy one. But on this one we do. So we do have a plus here. Okay. First we're going to plug into 2. So that's 2 squared is 4 minus 2, right? Plug in the 2 for x, so that'd be 4 minus 2. But now we got to subtract off this one. So that's going to be, and it depends on how you like to do it. I'm going to try to do it with skipping a few steps here. Hopefully you won't mind. It's minus a 1/2 squared, which is 1/4 again, right? I can't write a 4. This is one of the ugliest 4s I've ever seen. Okay, let me see if I can get that cleaned up a little bit here. It's going to mess up everything, but let me do it. Okay. This is worse than watching paint dry, isn't it? Okay. That's minus 1/4. That's plugging in this part minus this one. And then it's a minus 1/2 plugged in here, but it's a minus, so that makes a plus. Now I'm skipping some steps here just because it's so hard to write. So that's plus a 1/2. The reason it's a plus, when you're doing the lower one, is the minus of this. And that's minus a minus is plus 1/2. Okay. Now, let's go back and see if we can combine what we can combine. The minus 1/4 and another minus 1/4 adds up to minus 1/2, right? So these are going to wipe out. Those and that one are going to wipe out because minus 1/4 is plus 1/2 plus 1/2. 4 minus 2 is 2, and then add a 1/2 to it, you get 2.5. Now that to me is a perfectly good answer, but I bet you the book puts 5/2. Let's see who wins the bet. Either answer is perfectly fine with me. Let's see what they've got, please. Oh, yeah, the book says 5/2. Let me make sure I got it right. Do you see why that's true? Okay. Now, why they started you off with one that was so sort of bizarre, but it was. Now, here is the pictorial view of that. You see the absolute value here. You've shifted over from you had a horizontal shift 1 to the right. Actually, it turned out being 1/2 to the right for another reason. You had a vertical stretch by 2, and that made a, so you shifted over to 1/2. Okay, just take my word, and that's why the 1/2 here turned out where it was. I can't. Here we go. That's why your division point was 1/2 there. That's what your absolute value looks like. It's always a V shape. This one's a vertical stretch up and a shift by 1/2 to the right. Okay. And you're doing the area under there. So this is that first little triangle that you had here. And then this was the bigger triangle over here. They're both positive triangles, but you calculate them differently. Okay. That's example 2. Any questions on that before we leave it? Any questions? Okay. If not, let's clear the slide. Speak now or forever hold your peace because I can't get it back once I clear it. Any questions? Okay, let's clear the drawings. Now let's do it. Find the area of the region bounded by the graph of y is equal to 1 over x. Okay, there's your function, 1 over x. The x-axis, so I'm not going to write it down, but just remember that's another boundary. The vertical lines, x equal 1 and x equal e. Rather strange. So actually the x-axis is the same where y is equal to 0, right? Because that's the x-axis. So that's easier to write than me write the x-axis. Y is equal to 0. That means the x-axis, okay? And then x equal 1. And finally, strangely, x equal e, which I would never have guessed that's where they'd be going with this. But it's like, oh yeah, actually it's a very good place to go. That's an e. It doesn't look like an e, but just remember that's an e. Okay. Now, you're finding the area under a curve. Now, there's two things I want to ask for you. When you're finding areas, what must be true about your function? What must be true about the function? I'm not trying to keep away vampires. What am I trying to get you to say? Needs to be positive. Now, look at 1 over x here. There's your function. Is that always positive? The answer is always positive as long as x is positive, right? Well, look at this. Your x is always positive. X going from 1 to e. E is about 2.7 or so, you know. So yeah, x is always positive there. Now, here was the second thing I wanted you to point out. Because of that, what can x never be? Where does x live here in this function? In the denominator. And what's true about denominators? What can a denominator never be? What can your denominator never be? You can never divide by, come on, somebody, 0. Okay, so therefore, you have a function here. On the left-hand side of 0, this function is always negative. On the right-hand side of 0, the function is always positive. At 0, it's not defined. And not only is it not defined, of course it's not defined, but it's completely discontinuous. It's going very negative to the left of 0, very positive to the right of 0. So therefore, you could not have this function if this had been x going from -1 to e, because the function is not continuous over that interval. So from 1 to e, yeah, always positive, it's continuous there. They drew the picture in the book, and it's a perfectly good function. So we can do what they're asking us to do. And if we find the area under this function, which is y is equal f of x is 1 over x, this would be the area would be the definite integral from 1 to that strange little number e, irrational number e, of 1 over x dx. Now, this is seeing how good your memory is. Last week we did this. What is the antiderivative of 1 over x? This is not a time to make that as x to the minus 1. Because when you do x to the minus 1, and increase that by 1, it becomes x to the 0. But then the next step would be dividing by 0. You can't do it. This is not a rational function. It looks like a rational function. In fact, it is a rational function, but this is not a rational function you can take an antiderivative for. So what was a special case when the exponent is equal to -1? What is the value of this? The antiderivative of 1 over x. Does anyone remember? Please say yes, somebody. That's it, the natural log of x. And we're going to evaluate this from x equal 1 to x equal e. That's an ugly e. I don't know why the e's are writing so badly today. Okay, and how would you evaluate this? Put the e in for x. And what's the log of e? Does anyone remember? Log of e. Anybody? Log and exponential functions are inverse operations of each other. So if you take the log of e or the exponentiate a log, everything goes away and you're left with 1. Log of e is 1. Okay? Minus the log of 0. I'm sorry, the log of 1. Does anyone remember what the log of 1 is? Please say yes. Log of 1 is 0. Perfect. And 1 minus 0, I bet you they write this out in the book, is 1. Okay? So the area under that curve was exactly, precisely 1. Okay. Now, the pictures in the book, I don't know if my holding it up is going to make it any better. For those who don't have this book to see, there's that little portion of the curve, y is equal to 1 over x, evaluated from x equal 1 to e. E, remember, is 2.71, blah, 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 blah. It's an irrational number. So they drew it about right, and the area under there was exactly, precisely 1. All right. Any questions on that? Okay. Y'all aren't going to let me go over, are you? Okay. We've got what? 8 minutes? No. 9 minutes? 11 minutes. 11 minutes. No, wait, that's not right. Yeah, 11 minutes, I believe. Don't let me go over, folks, please. All right. Any questions on this before I leave the screen? So what I'm going to do is go back to my PowerPoint, which is 5.4, I believe we're in. Okay, here we go. We have to go back to current slide. All right, that was example 1, which we did. Now we're ready to hit, and if you're in the text, you're at the top of page 320. The mean value theorem for integrals. All right. You saw that the area of a region under a curve is always greater than the area, of the inscribed rectangle and less than the area of the circumscribed rectangle. Okay? Now, the mean value theorem for integrals states that somewhere in between those two rectangles, you will have the rectangle whose area is precisely equal to the area under that region of the curve. So if we did this one, and I wish they had shown the picture a little bit better, and what we have to do, I wish I could draw on this screen. They don't let me, okay? In my old computer, I could. Okay, if you did a rectangle that went under the minimum value there, and went there, that would be the area of the rectangle less than the area. The circumscribed rectangle would be the one that went from the top here, the maximum value across. That's the area of that one. And the area that's underneath this curve is in between those two. Okay? Well, they've drawn a rectangle here. And sure enough, looking at it, it looks like this green region here that's above the curve here seems to be about the same size as the pink region here that's above the curve. So this rectangle, we would think, has the same area as the area under the curve. If those two areas there are indeed equal, then that would be the rectangle that has exactly that. Okay. Now, if that's the case, that means there's some value C here that f of C right here times b minus a would be exactly the area under that curve. So to say that a different way, f of c times b minus a would be exactly the same as the integral between a and b of f of x dx. Okay. That's getting pretty close to what we call the mean value theorem. So let's see how they state it. Mean value theorem for integrals. If f is a continuous function on some closed interval a to b, not necessarily integrable, but definitely continuous on the closed interval a to b, then there has to be some number c that's also in that closed interval a to b, such that the integral from a to b of f of x dx is exactly that f of c times b minus a. Okay, basically say what we did before. F is continuous on the closed interval from a to b. There has to be some number c in that closed interval a to b, such that the area under the curve of f of x is exactly that f of c times the length b minus a. All right. They do a little proof here, okay? And they don't show it on the slide set. Well worth your looking at. Now, if you are not using this text, I bet you have a proof somewhere in your text of the mean value theorem for integrals. So take a look at that. This is a graphical illustration, but it's also an analytical illustration. So take a look at that. Since I don't have it on the slide set and I can't possibly, well, I can, but it would take all the rest of the time we had plus some, draw this on my that screen. That's just not doable. Now, here's what I suggest to you, though. Go to your calcview.com. Now, all of you can get there. Just go to calcview.com, calcview.com, and you should be able to find somewhere in there this, because you see that barcode over there at the other end of this block? That means they go into more detail there. So I bet you at calcview.com you can find this proof done. So if you want to see that proof, and I know all of you do, please go there and they'll walk you through it. I just can't possibly write all this on that drawing board. It would be miserable. Okay, so let's see. 5 minutes. Let's start talking about the average value of a function. Okay. The value that f of c in the mean value theorem for integrals is also sometimes called the average value of f on the interval from a to b. Okay. Now here is why. Okay. Now here again, this time it's a little bit wavier of a function. It goes up, down, and up again between A and B. Okay. Now here you actually have 3 C's that would fit the bill here. Either the C right here between A and B, or the C right here between A and B, or the C over here. It doesn't matter which one you choose, but that C would be f of C, any one of those C, because they all cross the function there, times B minus A would be the average value of the function. Okay? I mean, sorry, the f of C would be that value. Okay? The average value, because it's at this C, at that C, and that C, they all have the same value, and that value here would then represent the area under the curve. And if any one of those f of C times A minus B was equal to that, multiply both sides or divide both sides by B minus A, and you get that average value. So basically this is saying the definition of the average value of a function on an interval, if f is integrable, has to be integrable. That means you can integrate it on the closed interval A to B, then the average value of f on that interval is 1 over B minus A times the integral from A to B. And it doesn't matter which C you chose because the f at all those C's were the same, and that is the average value. That f of any one of those C's would be that. I'm not saying any C on there. I'm saying that C, or that C, because they're all the same values. That would be the average value of the function. Okay. Now, to see why the average value of the function is defined in that way, partition that interval A to B into n subintervals of equal width. Are we going to have time to do this? I don't think so. What do you think? I think this is almost. Let's go back next time and start with average value of the function. It'll be a little bit of a review, but not much. And we'll pick up and go from there because I don't think I can get through these two slides. And yes, it's what? They did. Excellent. Okay. Well, I've got you on the roll in my book, so you'll be on the roll from now on. So I'll see you tomorrow there, right? Okay. So let's see. Homework exercises from, wow, 5.4 is one long section. Okay, here's what you can do. This is starts on page 328 if you have this book. Either 5 or 7, they're both at Calc Cat. Any of the odds 9 through 20 or 33, they're all at Calc Cat. 17's at Calc View. Okay, either 35 or 37, they're both at Calc Cat. 35's at Calc View. Any of the odds 39 to 43, they're all at Calc Chat. 41's at Calc View. And then you can use the mean value theorem to do any of the odds 45 to 49. They're all at Calc Chat. 45's at Calc View. But hold off on the average value of the function. That's where we stop. So we'll stop there. So go as far as 49. Okay. Any questions on anything we did? Okay, we'll pick up with average value of the function next time. We'll hopefully, yeah. Say that one more time. The page number where those exercises were. Okay, I just had it. Page 328, and every one of those is on 328. The next page starts with 51. That's where we stop. So all on page 328. Exercise set 5.4. The first, any of the odds of the first 49. Okay. So next time, say again. Okay. All right, surely. Next time we'll finish 5.4 and get into a really fun thing, integration by substitution. I think you'll really enjoy that. We've moved right along in integration now. The slow part to me is that we've just done the summations and the limits and those kinds of things. From here on, I think you'll find it moves along a little more quickly. Okay. All right, good deal, folks. I think we are out of time. So I've got to sign off because I've got another class starting in 4 minutes. Okay. Take care. We'll see you Wednesday, okay? All righty. I'm going to end the recording. I mean, end Zoom, and I'll also end the recording.